Today we're going to look at an important class of polynomials known as Hermite polynomials. And these have lots of nice applications in differential equations, including solving some differential equations important in physics. Okay, so let's get to the definition, of which there are a couple of equivalent definitions. We'll use a recursive definition. So we'll define hn of x for n bigger than or equal to 0 by h of 0 is the constant polynomial 1. h1 of x is 2x, and then hn plus 1 of x is equal to 2x hn of x minus 2n hn minus 1 of x. So we've got this nice two-step recursion. Okay, so let's look at a couple of examples. So I guess we should probably start with h2 because we have h0 and h1. Okay, so h2 by our recursion will be 2x times h1 of x minus 2 times h0 of x. It's 2 because for h2 of x in this formula, n will be equal to 1. So putting this all together, we'll see that we get 4x squared minus 2. Okay, so there's h2 of x. And then let's look at h3 of x. So that's going to be equal to 2x h2 of x minus, well, it'll be 2 times 2, which is 4 times h1 of x. Okay, but then simplifying this out, we'll get 8x cubed minus 12x. And then similarly, we can calculate h4 of x via the recursion, and we'll see that we get 16x to the 4 minus 48x squared, and then plus 12. Okay, nice. So there, now we've got 5 examples of Hermite polynomials. The 0th, 1st, 2nd, 3rd, and 4th. Now, next up, we're going to prove that they satisfy a certain derivative relationship. That the derivative of the nth Hermite polynomial is 2n times the n minus first Hermite polynomial. But before we do that, let's look at some examples. Well, maybe starting here, notice that if we take the derivative of the first Hermite polynomial, we get twice the 0th Hermite polynomial. But that satisfies this rule right here. Now let's look at what's going on with the second Hermite polynomial. So note, if we take the derivative of the second Hermite polynomial, what will we get? We will get, let's see, 8 times x. But 8 times x is pretty clearly 4 times the first Hermite polynomial. In other words, 2 times 2 times the first Hermite polynomial. But now let's look at this third. So if we take the derivative of the third Hermite polynomial, h3, we'll get, let's see, that'll be 24x squared minus 12. But that's pretty clearly equal to 6 times h2 of x. And then you can check that the rule holds for h4 as well. So we've got some sort of evidence that this holds. Well, not much evidence, just the first couple of cases. But that'll at least set up the general argument, which we'll do by induction. Okay, so now we're ready for our first result, which we'll prove by induction. And that says for all n bigger than or equal to 1, the derivative of the nth Hermite polynomial is 2n times the n minus first Hermite polynomial. And we're going to do this by induction, but I'd like to note that our base case is done because we did some examples on the last board. So that means we just can start with an induction hypothesis. So our induction hypothesis will in fact be a strong induction hypothesis. And the motivation for needing that is the fact that we've got a two-step recursion right here. So it won't be enough to assume that the previous case is true. We have to assume that the previous cases are true. So we'll do it like this. So let's suppose for all m that are between 1 and k, we have this holding. So we've got hm prime of x is equal to 2 times m times hm minus 1 of x. So this holds for m equals 1, m equals 2, all the way up to m equals k. I guess that includes m equals k minus 1, which will be important. Okay, so next up, we're going to consider the next case. So we'll consider the derivative of the k plus first Hermite polynomial. But what I'll do is I'll expand out that k plus first Hermite polynomial using the defining recursion. So I'll have the derivative with respect to x, and then that thing expanded out will look like 2x times hk of x, and then it'll be minus 2k hk minus 1 of x. Good. And now let's take the derivative. Notice that we will have to use the product rule on this term because we have a 2x times hk of x. Okay, so let's do that. So we'll have 2 times hk of x. That's from taking the derivative of x plus 2x times h prime kx. Great. So that's from taking the derivative of the Hermite polynomial. And then we don't have to use the product rule over there because we're multiplying by a constant. So we'll get minus 2k hk minus 1 prime of x. Okay, so that is good, I think. So next up, what we'll do is use our induction hypothesis on h prime k and hk minus 1 prime. So let's see. I'll just bring this down. We have 2hk of x plus 2x, but hk prime can be written as 2k hk minus 1. So that's going to, in the end, give us a 4k times x, hk minus 1 of x. Okay, good. And then we'll use the rule on this as well. But here, m is replaced with k minus 1. So that'll give us a 2 times k minus 1, hk minus 2. So in the end, we'll have 4k times k minus 1 times hk minus 2 of x. And now we don't have any derivatives left. Okay, so what should we do from here? Well, notice that we've got 2k as a common factor of these last two terms. Let's maybe pull that out. So bringing this down, we have 2hk of x plus 2 times k, and then we'll be left with 2x hk minus 1 of x, and then minus, let's see what that'll be. It'll be 2 times k minus 1 hk minus 2 of x. Great. But look at what has been deposited for us. This stuff that's in parentheses is exactly in the form of something that we can apply the recursion to. In fact, it looks exactly like this, where n has been replaced with k minus 1. So that means we can replace this with hk of x. So look at what we've got, a 2hk and a 2khk. So putting that all together, we have 2 times k plus 1 times hk of x. But now, starting here and ending here is exactly what we needed to finish this induction step, which finishes the proof of this claim using induction. And now we're ready to move on to this second result, which says Hn is a solution of the following second-order linear homogeneous differential equation with non-constant coefficients. So that's a mouthful. But we've got y double prime minus 2x times y prime plus 2ny. So how are we going to do this? Well, simply, we're just going to stick Hn inside of this left-hand side of the differential equation, that differential operator, and see that it simplifies down to 0. Okay, so let's do that. So we'll have Hn double prime of x, and then minus 2x times Hn prime of x, and then plus 2n times h of x. And like I said, our goal is to simplify that down until we have 0. Okay, so how might we do this? Well, look, we've got a huge tool here, which is this previous result. So let's use that previous result a couple of times. So here we can apply the previous result twice to leave us with what? We'll have 4n times n minus 1 times hn minus 2 of x. So like I said, that's just from applying this result twice. Why twice? Well, because we've got a second derivative. And now let's apply it once here. So here we'll have minus 4n times x times hn minus 1 of x. And then finally, plus 2n times hn of x. Okay, great. Next up, I'd like to note that I can pull a 2n out of this entire thing. So let's do that. So pulling a 2n out of this whole thing will leave us with what? Well, we'll have 2 times n minus 1 times hn minus 2 of x minus 2x times hn minus 1 of x. And then that'll be plus hn of x. But now you can maybe see what's about to happen. Notice that this is exactly our defining recursion where n has been replaced with n minus 1 in this case. Well, also the sign has changed because the order of subtraction is opposite. So that being said, this will combine together to give us minus hn of x. But now this minus hn will cancel with this hn, leaving us with 0. But that means that our Hermite polynomial satisfied that differential equation, which means it is a solution to the differential equation. So our last result will be this kind of competing or equivalent definition of the Hermite polynomials, which is this. We've got hn is equal to minus 1 to the n e to the x squared times the nth derivative of e to the minus x squared. So I think this is pretty cool because we're like conjugating this derivative operator by those two exponential functions. Okay, so how are we going to go about this? Well, we'll simply show that this object right here indeed satisfies the defining recursion of the Hermite polynomials. Okay, so let's do that. So let's introduce a little bit of notation. So let's maybe set Pn of x equal to minus 1 to the n e to the x squared, and then the nth derivative with respect to x of e to the minus x squared. And like I said, we'll show that this object satisfies the defining recursion, which means it indeed has to be the same set of polynomials. Because solution to this recursion is unique. I guess we're not going to prove that part, but I think that's pretty clear. Okay, so let's look at P0 of x. So that's going to be minus 1 to the 0, which is 1. And then we'll have e to the x squared times the 0th derivative of e to the negative x squared, which is just the function itself. And so those multiply together kind of obviously to give us 1. Okay, so it's got the same first term at least. Maybe the same 0th term, I should say. Now let's look at the first term. So P1 of x, so that'll be minus 1 to the 1, which is minus 1. And then we have e to the x squared, and then the derivative, the first derivative of e to the minus x squared. So that'll be minus 2x, e to the minus x squared using the chain rule. So that simplifies to 2x, which is exactly what we needed it to do, in order to be this right here. Okay, so now let's make sure it satisfies the recursion. So let's look at Pn plus 1 of x and see if we can simplify it down to, well, it needs to be 2x Pn minus 2n Pn minus 1. Okay, so this is going to be minus 1 to the n plus 1. And then we have e to the x squared. And then we'll have the n plus first derivative, but I'm going to split that into the nth derivative of the first derivative of e to the minus x squared, because that's how derivatives work. Okay, and now I'll apply this derivative. So let's see what that'll leave us with. So we'll have a minus 1 to the n plus 1, e to the x squared. I'll have my nth derivative here. And then, it's pretty easy to take that derivative. That's going to give us minus 2x e to the minus x squared. Now I'm going to take this minus sign out and, cancel this down to a minus 1 to the n, and I'll take the 2 out as well. So that'll leave us 2 minus 1 to the n, and then I'll have e to the x squared, and then the derivative, well, the nth derivative of x times e to the minus x squared. And now I'm going to use a trick for taking repeated derivatives. And so this is like kind of a product rule for maybe higher order derivatives. Maybe I'll write it down here in the margin right here. Okay, and what does that say? Well, it says this. It says that the nth derivative of a function f times a function g is equal to the sum as k goes from 0 up to n of the binomial coefficient n choose k of the kth derivative of f and the n minus kth derivative of g. So that's the so-called Leibniz rule for higher derivatives. So we're going to use that on maybe this object right here, which I'm overlining in green. Okay, so what's that going to leave us with? So we've got a 2, we've got a minus 1 to the n, we've got an e to the x squared. That all just comes down. So we'll have n choose 0, and then the 0th derivative of x, and then the nth derivative of e to the minus x squared. So the 0th derivative of x is simply x. And then we've got, like I said, the nth derivative of e to the minus x squared. And then we add that to n choose 1, the first derivative of x, but the first derivative of x is 1, and then we'll have the n minus first derivative of e to the minus x squared. And then we'll have plus, well, n choose 2, the second derivative of x, oh, but that's 0, so we don't need to worry about it. Then the next term will be the third derivative of x, but that's also 0. In fact, all of the rest of the terms will give us 0 because we have higher derivatives of x. Okay, so now let's maybe start putting this together. So if we distribute this term right here on our first term, you'll see that, well, the x is to the left of the derivative, so we can pull it out, combine it with the 2, and we're left exactly with 2x times p sub n of x by definition. And then if we distribute this onto the second term, well, you see that we can pull a minus sign out to make the exponent of minus 1 correspond to the exponent of the derivative. And when we combine it together with this n, which I missed from the n choose 1, I think I said it out loud but didn't write it down, we get this minus 2n times pn minus 1. So minus 2n times pn minus 1 of x. Oh, but let's see what we've done. We've just shown that our polynomials satisfy the condition where the first two are the first two Hermite polynomials, and then they satisfy the two-step recursion thereafter. But that means our polynomials are in fact the Hermite polynomials. And so that proves this result. And that leaves us just with one last thing, and that's a homework exercise. So this is another important property of the Hermite polynomials, and that is they form a class of so-called orthogonal polynomials. And in this case, what does that mean? Well, there's a certain inner product where if you take the inner product of two Hermite polynomials that are not the same, you get 0, and if they are the same, well, you get a number. But that can be expressed by the following integral identity. So we've got the integral from minus infinity to infinity of the mth Hermite polynomial times the nth Hermite polynomial times e to the minus x squared is equal to 2 to the n factorial times the square root of pi times delta mn. So let's just recall that delta mn equals 1 if m is equal to n, and 0 if m is not equal to n. So this integral is mimicking the idea of a dot product, and orthogonality is like a generalization of the notion of perpendicular. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.